I am Anikate Koul, and today we'll be discussing the 23rd problem from the CP-31 sheet by TLE Eliminators under the 1200 rated problems. We'll be moving to the CP-31 sheet, and we can see that the 1200 rated parameter has been checked. I'll be scrolling down to find a clickable link to my problem. Let's begin. So the problem name is quite difficult, so I think I may not be able to pronounce it, but nevertheless, we can start reading the problem statement. It is no surprise Fischl speaks with a strange choice of words. However, this time, not even Oz, his raven friend, can interpret her expressions. Maybe you can help us understand what this young princess is saying. You are given a string of n lowercase Latin letters, the words that Fischl just spoke. You think that max of this string may help you find the meaning behind this message. The max of the string is defined as the shortest string that does not appear as a contiguous substring in the input. If multiple strings exist, the lexicographically smallest one is considered the max. Note that the empty substring does not count as a valid max. A string A is lexicographically smaller than a string B if and only if one of the following holds. A is a prefix of B, but A is not equal to B, or in the first position where A and B differ, the string A has a letter that appears earlier in the alphabet than the corresponding letter in B. A string A is a substring of string B if A can be obtained from B by deleting several characters from the beginning and several characters from the end, possibly 0 for both. Find out what the max of the string is. Now for the input format and the test cases, the first line of the test file would contain a single integer t denoting the number of test cases, which can go up to 10 power 3 or 1000. Then for every test case, the first line would contain an integer n, which describes the size of the word, and this value can go up till 1000 as well. Then the second line of each test case would contain n characters, which constitute the string, right? It is also given that the sum of n overall test cases will not exceed 1000. You have to output for every test case a single string which denotes the max of the given string, right? So as we have read the problem statement, we can move on to understand it. So it is given that for every test case you have two things, n and s. N is an integer which denotes the size, right? And it denotes the size of our string s. Now, according to the problem statement, string s is basically a word spoken by the main character in our problem statement. Now, what basically happens is we are asked to find the max of this string s, right? Now, let's see what max actually means. Let's say we are given a string which contains only lowercase English alphabets. Let's say the string was A C B A B D. Let's say this is our string, right? Now, max of the string is the smallest string s dash such that s dash is not a substring of s. This is the definition of max of a string, right? And by smallest, here I mean lexicographically smallest. And it is given in the question what lexicographically means. So let's say if I have two strings s1 and s2, s1 would be lexicographically smaller than s2 given one of these two conditions. The first one is that s1 is a prefix of s2. So let's say if s2 is a, b, c, d, then if s1 is a, or s1 is a, or s1 is a, b, or s1 is a, b, c. So all these are prefixes. Then s1 is smaller than s2 given that s1 is not equal to s2, right? If S1 is not equal to S2 and S1 is a prefix of S2, then we can say S1 is lexicographically smaller than S2. Or the other condition could be that on the first position, where let's say S1 of I is not equal to S2 of I, let's say I is the first position where this conditions comes into place, there S1 of I is less than S2 of I, right? Because here we are comparing characters and not strings. So that character in S1 is smaller, or it occurs before than S2 of I in our alphabetical order. So these are the two conditions for which we decide a smaller string or lexicographically smaller string. The definition of mix, as I said, is smallest string S dash such that S dash is not a substring of S. So let's say for this given string, if this is S, there are multiple substrings. There are multiple strings S dash which are not the substring of this string. So let's say XY. So XY is not a substring of this given S, right? But is it the smallest? That we have to check. So in our case, the smallest would be, I think, E. E is the smallest string because the string can have length 1 as well. So E is the smallest string which is not the substring of our given S. So as we have to output the max of a string, that is also the output format, basically one string per test case. Now as we have understood the problem statement, let's see a sample case to understand it better. Let's take this one. Okay, let's paste it here, remove any extra thing that we don't need, as well as increase the font size. Right, so let's remove this. This is N and this is S, right? So now we have to find the smallest string S dash such that S dash is not a substring of S, right? So let's start by checking all strings of length 1, right? So we can see here that all characters from A to Z are present in this string. You can check that for yourself. So that would mean that obviously any string of length 1 cannot be our answer. Now let's try checking strings of length 2. So what are the strings of length 2 in lexicographical order? So it is AA, AB, AC, AD, AE, so on, right? And then we would have BA, BB, so on. So if we check for AA, we can see here AA is present. If we check for AB, we can see AB is present. But if I check for AC, you can check that AC is nowhere present because there is only one C here and there is no A behind it. So AC string is not the substring of this given string, and also it is the smallest string S dash, which is not the substring of S. So therefore this AC is our mix. So mix equals to AC. And if we refer to our sample cases, we can see indeed AC is the max of our string. So as we have discussed the sample case, we can move on to discuss the expected time complexity. Now it is given that there is a bound of sum over n over all test cases, and that is less than equal to 1000, right? So instead of writing our time complexity as O of t into f of n, where f of n is a function of n, we can simply write it as O of f of n, because there is a bound over sum of all test cases, therefore I do not need to consider t. Now we are also given that n can go up till 1000, sum of n actually can go up till 1000, Also, we know that on Codeforces in 1 second, we can run up to 10 power 8 elementary operations in 1 second. So our limit would be 10 power 8. Now, if I run a time complexity O of n, then this would be 1000 operations and this would run perfectly fine. O of n square would run around 10 power 6, right? And this will also run pretty fine. But O of n cube will take a time complexity of will take the operations that would be in the range of 10 power 9, and this will not run, right, because it is larger than 10 power 8. So we want an algorithm which runs in the vicinity of O of n or O of n square, right? So now let's discuss the solution. So let's make some observations that would lead us to the correct algorithm. The first thing is that it is given that for any test case, a string may be of length at a max 1000, apart from the given fact that sum of n is less than equal to 1000, right? So let's keep this thing in mind, right? Now, if we try to brute force over all possible strings of that could be substring of this string of given length n, then it would be very difficult, right? Because we don't know the length and we don't know where to look. So it would be very difficult for us to find a max randomly. What we can do is try to reduce our search space. So what we can do is try to understand till what length do we have to check, right? So if I know that I have to check till some length x, right? So what I can do is I can run a loop from 1 to x, and for every value in this, so let's say I goes from 1 to x, so then I can generate all possible strings of given length I and then check whether they're present in my string or not. But the question is, how do I find this x, right? So let's perform some calculations and try to understand this bound of x, right? So we have, let's say in the worst case, a string of length 1000, n is equals to 1000, right? How many strings would be there which would have length 1, substrings to be specific? How many substrings of a string of length n would be there which would have length 1? N, right? Because let's say I have a string of length 4, A, B, C, D. How many substrings are there which have a length 1? 4, right? Which are A, B, C, and D. Similarly, if I would ask you how many strings or substrings are there of a string of length n that have a length equal to 2, it would be n minus 1, right? And if we take this given example, A, B, C, D, we would have 3 substrings of length 2, which would be A, B, B, C, and C, D. And we can also generalize this formula that for a given string of length n, there would be n minus L plus 1 substrings of length L. This is our formula, right? For a given string of length n, there would be n minus L plus 1 substrings of length L. Now, according to this, we will make another observation. Let's say I have a substring of length L, right? There is a random substring of length L, right? Now, if I consider this substring on its own, let's say it has length 3. how many possible strings can I generate of length 3? This is my question now. So if I have a string of length 3, how many possible strings can I generate, right? So I have 3 positions here. This position can be filled in 26 ways. This position can be filled in 26 ways, and this position can be filled in 26 ways, right? Because we are just considering lowercase English alphabets. So can I say there will be 26 power 3 ways? Similarly, if there was a string of length L, there will be 26 ways to fill the first position, 26 ways to fill the second position, 26 ways to fill the third position, so on till 26 ways to fill the last position. And that would result to a total number of 26 power L substrings or 26 power L possible strings. Now we know these through these two things, that number of possible substrings of length L are n minus L plus 1, and number of possible strings of a given length L are 26 power L, right? So let's try to have a bound, right? So if I say I have to check the length X only, that I said above here, that I want to check for all substrings till length X. So how many possible strings do I have to check for length 1? 26. Then I would have to check for 26 square strings of length 2. Similarly, 26 power 3 strings of length 3, 26 power 4 strings of length 4, so on till 26 power n strings of length n, right? These are total number of possible strings of given lengths. So I can have 26 strings of length 1, 26 power 2 strings of length 2, 26 power 3 strings of length 3, 26 power 4 strings of length 4, and so on till 26 power n strings of length n. But at the same time, how many possible substrings can occur for a given string? I have to check also that also, right? N strings, n substrings can occur of length 1, n minus 1 substrings can occur of length 2, n minus 2 substrings can occur of length 3, n minus 3 substrings can occur of length 4, and so on till one substring can occur till length n. So these are my numbers that I need to consider, right? But there is one important relation which will help us solve the problem. The relation is that, let's say there are some val1 number of possible strings of length x, right? And there are val2 number of substrings that are present in my string s, right? Let's say if val1 is greater than val2, doesn't that mean that there would always exist some string of length x that is not a substring of s? Let me repeat it again so that it is better clear. I am saying, let's say there are val1 number of strings possible of length x, and there are val2 number of substrings of a given string s. If val1 is greater than val2, then that means always there would be some string of length x that would not be a substring of our string s. This is my assumption. And this is a fact basically, because if I take a string of length 30, let's say, right? How many substrings can it have of length 2? It can have 29 substrings of length 2. But how many strings are possible of length 2? 26 square, 676. There can be 676 possible strings of length 2, but there are only 29 present in my string. That means there must exist at least at least one string of length 2 that is not present in my string S, right? This is pretty clear. So what can I say? I can say I have to find a given x such that 26 plus 26 square plus 26 cube plus 26 power 4 so on till 26 power x is greater than n plus n minus 1 plus n minus 2 so on till n minus x plus 1, right? Because these are the total number of, okay, let me draw that again. Yes, these are the total number of substrings present in my string S which are less than or equal to the length of x, right? So these are the number of substrings of length 1, of length 2, of length 3, so on till length x. So this sum is the total number of substrings present in S which are of length less than or equal to x. And this sum is the total number of strings possible of length less than equal to x, right? So at the smallest x where this condition comes out to be true, that this LHS is greater than the given RHS, I can say that I have to check only till that size, because if I check till that size I will have at least one string which will be not present in my given string S, right? So let's do that manually, because we know n is only till 1000. So I can put the values of 1000 here, and I know because it is going in exponential format, it won't go that large. So I can do a brute force. So if n is equal to 1, then what can I say is 26 greater than 1000. That is not true. If n is equal to 2, then 26 plus 26 square is greater than 1000, which is 26 plus 676 is greater than 1000, or this would be equal to 12 and then 90702 greater than 1000, which is also false. And 26 plus 26 square plus 26 cube, okay, so I should not have written 1000 here, actually that is a mistake. Let's correct it. N plus n minus 1, right? So 1000 plus 999, which is 1999, and still the inequality is false. And here it would be 1000 plus 999 plus 998, and this would be equal to 26 plus 676 plus some value. So what I can do is quickly jump into my calculator and figure out what this value is. So 26 cube is equal to 17,576, and this value is equal to 1000 plus 990. So what I can say is this value is 1 less than 1000, this value is 2 less than 1000, so the sum would be 3 less than 1000, 3000, so that would be 2997. And I don't need to calculate the whole LHS, because 2997 is itself smaller than 17,576. So I know that this inequality is true. So I can say that if I brute force over all strings of length 1 till 3, then I will always find at least one string which is not the substring of our original string S. And this will always hold true, as I have already proved it with my calculations above. Right. So this is my final algorithm, that brute force over all possible strings of length 1, 2, and 3, and check for every string whether it is a substring of my given string S or not. If it is not, then the first string that is not the substring of S in lexicographical order is my max. So now let's discuss the time complexity of it. Now what I'm doing is running a loop of this much, right? So let's finally calculate what this value is. So again, let me hop onto my calculator and quickly calculate this sum, which is equal to 26 plus 676 plus 17,576, and this comes out to be roughly 18,278, right? So what I'll do, I will have to run a loop these many times, and I would better say that I have to iterate these many times. And every time what I would do is I would search in my string S whether the string formed is a substring or not. So basically what I do, that I run a loop these many times, I form some string S dash. Now I check if S dash is a substring of S or not. So total number of operations would be 18,278 into n, because I would need O of n time to check whether this S dash is a substring of S or not, right? And I would do that 18,278 times. So my total time complexity comes out to be O of 18,278 into n. I'm not ignoring this value because this value is quite large. But what I can do is try to calculate the number of operations it would take. So that would be 18,278 into 1000, because sum of n over test cases can go up to 1000, and that would be 1.8 into 10 power 7, and this is well below 10 power 8. So I can say yes, this algorithm will run pretty fine. Now as you have discussed the problem solution, we can move on to the implementation. So the implementation is exactly the same as we discussed in the solution. So first of all, what we do is take in the input for the number of test cases. Then for each test case, I take in the input for the size of our string and then the string itself. And then this string max stores our final answer. So this is our final answer. Now what we do is initially check that is there any single character that is missing from our string S. So how do we check that? For every character C from A to Z, we check if S dot find of C returns string of npos. Npos is returned from this find function if it does not find any occurrence of the given string or character in string S, right? So if that is the case, we write that our max is this character, and then we simply break. And this loop will take uh, O of 26 into n. Why? Because this outer loop runs 26 times, and this find function takes O of n time to search. So in total, this would take O of 26 into n. We can write here that this is O of n, right? Now, if we don't find anything, what happens is we move further. So you might be thinking that why don't I just print my answer here if I found my max? But I'll show you that if I had found my answer here, it won't get updated in this loop or in the consecutive loops. I've just now written the if conditions in order to simplify my implementation. We'll see that. So now what I do is check for all strings combinations of length 2. So I run two nested loops, each going from A to Z. Now I concatenate those two characters to calculate my string temp, and now I check my string temp inside my string is. Again, first of all, I check if max is empty. So if max is empty, that means it has not been updated still, and that also means that I have not found my answer. If I have found my answer, then it won't move further. Like this loop will not update my max if I had found the answer earlier. So if I have not found my answer earlier and s dot find of temp again returns string of npos, that means it has not found any occurrence of temp inside the string s, it gets updated to this max. Right. Great. Again, you might think why I have not used a break statement here, because if it gets updated if it gets updated here, again max will no longer be an empty string, so it won't get updated again. So again, as I said, this find function takes O of n time, and we have two nested loops of 26 each. So that would make our time complexity to be 26 power 2 into n. And now again similar thing, as we said, we have to check up to all strings of length 3. Again, I run 3 nested loops, which will help me find all possible strings of length 3. So this string temp is again the concatenation of C1, C2, C3, which is after all the iterations giving me all possible strings of length 3. Again, the similar thing, if max is empty, that means I have not found my answer still. Then I will check for temp inside s, and if it returns string of npos, that means it is not present. So I'll update my max to be equal to temp. The similar thing, just another nested loop. So this takes 26 cube into n time, right? And at last I print my max. So here the total time complexity comes out to be O of 26 into n plus 26 square into n and 26 plus 26 cube into n. And as we discussed earlier, that was equal to 18278 into n, right? And the total space complexity comes out to be O of n, because the only space that we are using is of this string s, and this string s is of size n. You may ask why I'm not adding the space for max and for these temp. They won't really matter, because what we can do is uh, take this temp outside of these loops, and again they won't take extra space, they'll be just being reassigned again and again. So the space would be linear in any case, or it will be a small multiple of n, which we can ignore, right? So we can update our implementation, and that will help us increase or decrease the space complexity. So if we just take out our temps outside, it is fine to go. Now, for the ending remarks, I would like to state that this problem was quite interesting for the fact that it required us to narrow down our search space. So initially we would be searching for all possible strings, but then using some clever observation and mathematical proofs, we were able to see that we need to check only for strings of length 1 to 3, and that would always contain an answer. So I hope you like the solution, and thank you.